Good morning, everyone. Today we are going to talk about the mechanics of deformable bodies for the MTECH students. We will be following the syllabus provided by VTU. To begin with, the first module deals with theory of elasticity, the introduction part. Before we start off with the syllabus directly, let us understand what is this elasticity. So the whole module deals with mechanics of deformable bodies. We're talking about bodies that are going to undergo deformation. Now, if you remember in SOM, if you can recollect from your BE, we had spoken about elasticity that was given by Young's modulus. Now, what is elasticity? If any external forces producing deformation, if it does not exceed a certain limit, and upon the removal of these forces, if the deformation disappears, then it is called as a perfectly elastic body. Here we talk about the deformation not exceeding a certain limit. So this is a statement that was given by the Hooke's law, that stress is directly proportional to strain within the proportional limit. That is, within this particular limit, that called the proportional limit, stress and strain are directly proportional. If you apply a certain amount of external force, there is going to be some stress that is going to be created in the body, followed by strain. Upon the removal of the force, the stress and strain reduces to zero. That is, the deformation comes back to its original. Let us say if a particular body is present, you have applied some force, it has undergone a deformation, the body comes back to its original position upon removal of forces. So this occurs only within the proportional limit. If you exceed the proportional limit, then the body is not called as perfectly elastic, because stress and strain are no longer proportional with respect to each other. Now, talking about the stress at a point, uh, for any given body, there are going to be two types of forces that are going to be produced. One is a surface force, and the next one is a body force. So the topic that we are going to start off with is stress at a point. For this particular one, we have two forces that are going to be produced. The first one is called as the surface forces. The name itself tells you what these kind of forces are. And the second one is nothing but the body forces that are going to be generated. First, this surface force, it acts on the boundaries of the body, and the body forces are going to be distributed throughout the volume of the body. These applied forces are resisted by a system of stresses throughout the body. Alright, so the state of stress at any given point of a continuous body, we talk with respect to a continuous body, is determined entirely by the components of stress in three mutually perpendicular planes. So we talk about three mutually perpendicular planes. That is nothing but x, y, and z. We have the coordinate axis and then three mutually perpendicular planes. The planes are going to be perpendicular to the coordinate directions, obviously 90 degrees, and then the stress at a point on any plane section throughout the point is going to be defined as force per unit area transmitted through that section at a point. The general definition of stress is nothing but force per unit area. Say if you have a particular body like this, say it has an area A. The area for this particular body is A, and the force that is going to be applied is F. Then stress is defined as force per unit area. So the units is going to be Newton per meter square, or Newton per mm square, or kilonewton per meter square. Okay. The stress components are going to be a function of both the position of the point in the body and the orientation of the plane passed through that particular point. So we talk about the point in the body as well as the orientation with respect to which the plane is going to be there. Each stress component can be resolved into three components along three coordinate axes. So we are going to have three components and then three coordinate axes. So if you want to represent the components of stress at a particular point, that is the stress tensor, then you are going to have 9 components of stress. Okay, so 3 into 3, it is going to be 9. The 9 components of stress, it is used to define the state of stress at any given point. As you know, stress is defined using this, denoted using the symbol sigma. So sigma is equal to force by area. We have 3 axes, x, y, z. So when in stress, we are going to have normal stress, that is going to be denoted by sigma, and then this normal stress is something that is going to act at every single plane, that is on x-axis, y-axis and z-axis. Then we are going to have a shearing stress represented by tau. So, shearing stress, if we can recollect from SOM, it is with respect to 2 planes. So, one is going to move in one direction, the other one is going to move in the other direction. Here, we are going to have a shear that is going to be created, usually at the corners of a body. So, this is how a shearing stress is going to be denoted. Now, we are going to define the components of stress, or I can call it as a stress tensor, where we will be having 9 components. If you want to define it with respect to in form of a matrix, you have normal components. This is very easy to remember. So along the diagonal, principal diagonal elements, you have sigma x, sigma y, and then sigma z. For the other places, you are going to have the shear stress, that is nothing but tau. And then they should be denoted with respect to the components. This is nothing but your sigma x. So first it is going to be with respect to x-axis, y-axis, then z-axis. So here it is tau x y, tau x z. Here it is tau y x, and then here it is tau, sorry, it is tau yz. Then here it is tau zx. Here it is tau zy. If you can see the pattern, these components are going to be equal. Yes, they are going to be equal. We can write that tau xy is equal to tau yx. Tau yz is equal to tau zy, and then tau xz is equal to tau zx. So we have normal stresses as well as the shearing stresses. This forms the stress tensor. Say I'm going to write it in the form of a 3D diagram. Then